So we finally made it to our last unit, which is going to be about radicals. So we're going to start by first going over what a radical expression is. So we'll define those. We're going to also talk about the domains of those, which we already have seen. And then we're going to start this process of simplifying them. And then our remaining sections are just going to build on that. So we've worked with exponents a lot already in this course. And we've already know that that exponent is representing repeated multiplication. So if we take 6 squared, it's the same thing as 6 times 6, which we know is 36. So just like we have our tools to reverse addition, subtraction, multiplication, and division, we need to be able to reverse these powers. So the opposite of taking a square is going to be taking a square root. So these two operations are going to cancel each other out. So we often call them an inverse. So the way you can think of this is we know 6 squared is 36. This is equivalent to rewriting a different expression by saying the square root of 36 is 6. So essentially, these square and square roots will cancel each other out. Okay. And really, the exact idea extends to higher powers. So if we have 2 to the third, it means 2 times 2 times 2, which we know is equal to 8. So to inverse this cube power, third power, we take a cube root. So the way we indicate that it's a cube root is we put a little 3 right here. Okay. So for a square, you won't see a number inside of there for a square root. That automatically means that there's just a 2 sitting in here. So really, in general, the nth root of some number a, which is written with an n right here in this little bracket, is a number whose nth power equals a. So what we can say is that we have the nth root of a equals b. You can rewrite as an expression by instead raising both of these to the nth power. So the nth and n root cancel each other out and give you a is b to the n. So we're always able to go back and forth between these. Now this specific expression is often called a radical, and there are different names for each of these. So just to kind of put those pieces into perspective, this value of n is called our index. This symbol that we're going to be using here is a radical symbol. And then the thing underneath the radical is called the radicand. Okay. So you'll often hear those words referred to each other, but this way you know what each piece represents. Okay. So let's get some practice. Let's try to just find each of these given roots. So again, we want this to equal something. It's going to be a number in the end, and we have to figure out what that number is. So because we have a cube root, we're looking for a number that multiplied by itself 3 times will give us 125. So the way I'm going to start writing these is by figuring out how I can rewrite 125. So you're definitely going to need a calculator for some of these numbers. But if you take 5 times 5 times 5, it gives you 125. And now here, the cube root and these cube cancel each other out. And so this is ultimately equal to 5. Okay. And the way you can check yourself is you can say the cube root of 125 is equal to 5. And that's because 125 is 5 to the third. So you can always check that you did find this correctly. So now for this next one, we have the 4th root of 16. Again, this is equal to some number. I need a number multiplied by itself 4 times to give us 16. And if you take 2 times 2 times 2 times 2, it is indeed going to equal 16. So again, our 4th root and 4th power undo each other, and this leaves us with a 2. Okay. So we have a couple other definitions. If we have an even number as that index, and as long as the thing underneath the radical is greater than 0 or equal to 0 for an even root, then just the nth root of a is called the principal nth root. If you take the negative in front of it, it's called the negative nth root. So this is going to come into play a little bit later on. But the one thing you want to keep in mind is, we've talked about this before, if you take the square root of a negative number, it does not result in something real, because there isn't a number that times by itself. Like a positive times a positive gives you a positive. If you take a negative and times it by a negative, it still gives you a positive. So there's no way I could put a number, times it by itself an even number times, and get a negative in there. So these are not real numbers. We're going to see that they're imaginary towards the end of this unit. But this is something we have to keep in mind. We really want to be working with real numbers. So a square root can't do that. A fourth root can't do that. A sixth root, an eighth root, any even number, you cannot have negative values underneath the radical. You can have the square root of 0. That's not a problem. Fourth root of 0, no issues. But we cannot take even roots of negative numbers. So this is going to be how we end up finding the domains for each of these functions. Now, on the opposite hand, though, we can take odd roots of negative numbers. So if you have negative 2 to the third, you're just multiplying negative 2 3 times, you get a negative value from doing this. So there's absolutely no issue to have a negative value under an odd root. Okay? It's only when we have even roots that we run into issues. So let's just try some examples. Let's keep working with these. We want to find each root if it exists. So for this first one, we have a minus sign on the outside, so that's no issue. And we want to take the square root of negative 81. So remember, you want to do things inside. Not really parentheses here, but you're going to see that these relate to exponents. So this is really like you're taking negative 1 and timesing it by this operation. So that minus sign is dealt with afterwards. So on the inside, 81 can be written as 9 squared. So the square and square root cancel. And that minus sign just stays out front, so it becomes negative 9. For this next one, we have the cube root of 216. So I need a number times itself 3 times. That gives us 216. So if you take 6 times 6, it's 36. Times it by 6 again, you'll find out it's 216. So the inside I can write as 6 to the third. And again, the cube and cube root cancel and leave us with just 6. Okay. For this next one, we run into a bit of an issue. So we've got a square root. So again, no number in there indicates that the index is a 2. And we have a problem because we have a negative sign underneath. So ultimately, we will be able to work with this when we talk about complex numbers. But for now, we're just going to say it's not a real number. So we can't actually find this root. For the next one, now we have the cube root of 27. And since it's an odd number, we have no problems with a negative underneath. So I need a number times itself 3 times to give us negative 27. And that ultimately will be negative 3. Negative 3 times negative 3 is positive 9. Times negative 3 is negative 27. So again, the cube and cube root cancel, and we're just left with negative 3. Okay. For this next one, we've got a fraction, which is never as nice. So what I want to do is I'm going to actually use some of our exponent properties. And again, we're going to discuss those again in the next section. I want to think about that numerator. So 64 is 4 to the third power. And 27 is 3 to the third power. So what we can actually do is remember one of our properties of exponents from way long ago. Keep writing the wrong number, is we can distribute that power over a fraction. So this is really 4/3 to the third power. And again, the third power and that cube root cancel. So we end up with 4/3. Okay. In reality, what we're going to see in the next section is you can go ahead and take the radical on each of these pieces and still lead to 4/3. Okay. So now that we have a little bit of a hand of actually evaluating these, we want to talk about the domains of these radical expressions. We have discussed them, I think, back in chapter 2 when we started talking about functions. And it deals with these even roots not being allowed negative signs underneath. So we need to make sure when we have an even root that what's underneath the radical is greater than or equal to 0. When you have an odd root, you have absolutely no issues at all. So let's try a couple examples. For this first one, we want to find and state the domain in interval notation. And so again, no index there means that it's a 2. So since it is an even root, we need the expression underneath the radical to be greater than or equal to 0. Okay? And this would be fine if it doesn't ask you, or it just asks for an inequality, but because we need to put in interval notation, let's go ahead and graph a number line. So 0 is an important number. We can equal it because of that bar, and we can take all x values greater than or equal to 0. So we can take everything over here. So in interval notation, the domain would be starting at 0, we can equal it, and then go to positive infinity. For this next one, we have a cube root. And thankfully for a cube root, I have no issues. It's perfectly fine if this expression is negative, if this expression is 0, or this expression is positive. So really, since there are no issues, we can plug whatever we want in for x. Okay. So as a result, the domain is all real numbers. And what that looks like in interval notation is you can take anything from negative infinity to positive infinity. Okay. Let's try one more. We're going to go back to an even root. So again, I need the expression underneath this radical to be greater than or equal to 0. And so unfortunately for this one, we do have to solve this inequality. You can go about this any way you want. I'm going to start, remember, we want to get x by itself. So I'm going to move this 5 to the other side. So I'm going to go ahead and subtract it. And that leaves us with negative 2x is greater than or equal to negative 5. And then we need to get x on its own, so we go ahead and divide by negative 2 to make those cancel. So we're left with x, and then if you take negative 5 divided by negative 2, the negatives cancel out. But the thing you have to remember is you need to flip the sign. So because we divided by a negative, gotta flip that inequality. So what this tells us is we can take all values less than or equal to 5/2. So again, I need to write this in interval notation, so let's go ahead and do a number line. 5/2 is our important number. We can equal it, and I can take x values up to that point. So we would shade to the left. So our domain is going from negative infinity to positive 5/2. Another thing you could also do that I think might be a little bit easier, you have 5 minus 2x needs to be greater than or equal to 0. At this step, it's probably a little bit easier to add the 2x to the other side. So this way it makes the number in front of the x positive, and you don't have to worry about flipping signs. Because now when you divide by 2, you still end up with the same thing. Your x is less than or equal to 5/2. That's the biggest we could be. Okay. So the very last thing we're going to do is really kind of setting you up if you have to go on to the next math course from this class. Our book kind of has the understanding that when we're working with variables, we're making sure that the numbers we're plugging in work with this domain. But I do really want to emphasize this because it's a really important quantity. So when we have the expression the square root of a squared, everything I've done so far has told us that the square and square root cancel each other out. And all of the examples we've done have worked out to that. But it's really not 100% true. So what I'm going to do is I'm going to look at two examples. So the first one, if I take the square root of 6 squared, well, 6 squared is 36. So I have no issues. Square root of 36 is 6. So indeed, the square and square root cancel, and you got exactly the number that was underneath it. But if I look at the square root of negative 6 squared, and I do the same thing, negative 6 to the second power is positive 36. When I take the square root of positive 36, I get 6. So unfortunately here, that square and square root didn't just cancel. What happened is this minus had to change to a positive after we went and took the square root. So in reality, what happens is when you have the square root of something squared, you really get the absolute value of that number. So it's guaranteeing that we have a positive output. So that's something we want to happen, or it could be 0 as an output. So you want to be careful, especially in your homework. It might yell at you a little bit when you're dealing with these expressions. If you ever get something wrong, just try putting absolute values around it or changing the sign that's in front of it, and that might correct your mistake. But this is a really important concept that the square and square root, although they do cancel each other out, it really leaves you with the absolute value of that thing, because an even root is never going to give you something negative. It's always going to give you something positive. If you have a minus sign in front, that's a little different. So we'll see a couple examples of how to work with this. So we're going to simplify each of these expressions. So in this first one, square root of 12 squared, square and square root just cancel each other out, give us 12. Here's where we run into that issue. Square root of negative 12 squared, I can't just say they cancel and give me negative 12 because it is an even root. So really what happens is I would recommend actually doing that inside first. It's the square root of positive 144, which gives us positive 12 as an output. So really in both of these, what you could do is you can say they cancel each other out, and it gives you the absolute value of 12, which is 12. Here, you can say that they cancel each other out, but you get the absolute value of negative 12. And again, all that does is it turns negative values positive. Okay. For these next two, because they're odd roots, we don't have to worry about the same thing. So here, fifth root, fifth power, cancel each other out, just give us the 8. And again, fifth and fifth root cancel each other out, just give us that negative 8. Because it's an odd power, we have no issues. Okay, it's only even that poses problems. So let's just try a couple more. For this first one, we've got negative 6 root of negative 8 to the 6. And again, I don't want to say that the 6 and 6 root just cancel each other out just yet. That minus sign is going to stay attached in the front. So you could plug this into your calculator, but this is where taking negative 8 to the 6th power would be a gigantic number. So the 6 and 6 root cancel each other out, but we have to take the absolute value of whatever this base is here. Okay? And what that does, the absolute value of negative 8 is positive 8, but the minus sign in front just immediately gives us negative 8 as an answer. Okay? For this next one, 10th and 10th root also cancel each other out. And so this is where your book kind of takes some liberty. We would say that this is just y, and there's no problems, we're going to assume that y was a right value to make this expression make sense. But in reality, what you do get is, because it's an even root, we get the absolute value of y to just guarantee that it's a positive number. If you mess those on a test or anything, it's not a super big deal. And especially when you see in our later sections, we kind of just assume that the variables take on appropriate numbers. Okay. For this next one, same idea. The 4 and 4th root cancel each other out. So we would get the absolute value of negative c, but that negative inside does nothing. So we would put absolute values around it to be as precise as we can. If you left it with the minus sign in the middle, not super essential either. They are the same thing. Okay. Now this next one, a little bit trickier, and it actually should be a slightly different number here. Made a slight typo. So this should be x to the 36 on the inside. So I don't have the same thing. I have a higher power on the inside than my root, so they don't quite cancel. So what I'm going to do, this is also leading into our next couple sections. I want to rewrite this inside. And so I want to rewrite it using this index of 4. So if you think of the number 36, you can think of that as 9 times 4. And then one of our exponent properties, we're going to actually reverse. If you multiply two exponents, that means you had a power to a power. So we can write x to the 9 times 4 as x to the 9th to the 4th power. And so in doing so, we now have a 4th root, 4th power. They cancel each other out, and we end up with x to the 9th. And again, because it was an even root all the way back here at the beginning, we want to put some absolute values around it just to be certain that it gives us a correct output. Okay. So in your homework, if you get marked wrong for anything, especially on these later problems, just try putting these absolute value bars around it. It probably should correct the issue. When we start talking about simplifying more complex radicals, then we kind of just, again, take for granted that we're assuming the variables make sense from the beginning. We don't need to worry about these absolute values.